Let us look at our second order example once again. We have the differential equation which describes a system. The differential equation is d square plus 5d plus 6 operating on x equals d plus 1 operating on u. U is the input and x is the response. For this, after taking Laplace transformation and looking at only one part of x of s, we got the expression that xs divided by u of s was given by s plus 1 divided by s plus 2 into s plus 3. We factorized the s squared plus 5s plus 6 into two factors, s plus 2 and s plus 3, and this is what I said was the transfer function, and it is represented on a pole 0 diagram as shown here. And in general there may be a multiplying coefficient in front which also can be indicated on the pole 0 diagram. Now with the help of this transfer function, what is it that one can say about the system behavior without doing computations? Qualitatively, what is it that one can say? Now of course what one can say depends on what one has studied beforehand and upon the experience that you have had looking at transfer functions like this. Later on we will look at what is called the frequency response of a system, and we will see that from the transfer function one can immediately get quite a lot of information about the frequency response of the system. But at the moment we will look at something else. Now you will remember that when we obtained the transfer function, we ignored some terms, or alternately we only looked at one part of the response transform. Let me go through it again very quickly. We have d square plus 5d plus 6 acting on x equal to d plus 1 acting on u. Applying the Laplace transformation, what do we get? On the left hand side we got s squared plus 5s plus 6 multiplying the Laplace transform of the response capital X of s, plus we got some terms containing the initial conditions of x, x0 and dx0 in this case. So let us write down that those set of terms together as, let us say, p bar of s, where the p suggests that it is a polynomial. Indeed it is a polynomial of degree 1, as you can check. So this is the thing that we get on the right hand side, the transform of x of s multiplied by s squared plus 5s plus 6, which can be obtained from d square plus 5d plus 6 by simply replacing d by s, and this is because of the derivative property of the Laplace transformation. On the right hand side what did we get? Similarly to the left hand side, the d plus 1 gives rise to s plus 1 multiplied by u of s. So s plus 1 multiplies the input transform, plus we have a term which contains the initial values of the input, because the input is getting differentiated on the right hand side. So let us write that down as q bar of s, and in fact I am going to write down the coefficient of x of s as ps and the coefficient of us as qs. So if I do that, then the equation that I get can be written as ps x of s plus p bar of s equals qs u of s plus q bar of s, where p and q are polynomials in s. They correspond to the operators. So the original differential equation, if it was pd acting on x equal to qd acting on u, then this ps appears here multiplying xs, qs appears here multiplying us, and then you have these two additional polynomials p bar and q bar, which involve or which depend on the initial values of the response and the input respectively. And therefore solving for x of s, we get three terms. One term is simply qs divided by ps multiplying us. The second term would be, let us say, plus q bar of s divided by ps, and the third term will be minus p bar of s divided by ps. Now what we have been looking at, or what we look at, or what we consider when we talk about the transfer function, is only this part, qs by ps multiplying us. We are not looking at the other two parts. There is this part q bar s divided by ps, which is not 0 if initial values of the input are not 0 and there are derivatives of input on the right hand side. The second term that we are not looking at is p bar of s, has numerator p bar of s. P bar of s is 0 if the initial values of the response are 0. So we can say that we will get only this part, namely qs by ps into us, if initial values of the response and the input are 0, but that will not be the case in general. So it is better to say and think that we are only looking at a part of the response transform, namely the part which does not involve the initial values of the response and the initial values of the input, but involves only the Laplace transform of the input, and that is multiplied by a ratio of two polynomials qs by ps, and this qs by ps is what we call the transfer function of the system. And as I told you earlier, in the control literature, the letter g of s, capital G of s, is very often used to denote a transfer function of what is called the forward path of the control system. Of course, if it is the feedback path, then the transfer function is labeled as h of s usually. So then we have the transfer function of the system g of s equal to qs by ps, and you can say that it gives you one part of the response when it is multiplied by the input transform. So remember that the transfer function does not give you the complete information about the response transform. It only gives you one part of the response transform. Of course, you can think about this and see that if I know ps, then I can find out the expression for p bar of s. Of course, p bar of s will involve initial values of x, but knowing the polynomial pd, I can obtain p bar of s. Similarly, knowing the polynomial qs or qd, I can obtain the polynomial q bar of s. So in that sense, if I am given the transfer function like this as a ratio of two polynomials, from that I can write down the two parts or the two terms which I have not looked at, or which we are not looking at when we talk about the transfer function. And as I told you earlier, from qs by ps as transfer function, we can easily go back to the differential equation p dx equal to q du. So we can recover the differential equation from the transfer function. Now, what information can we get about the system behavior from the transfer function? That is what we would like to look at for a little while. Remember, we are not going to look at frequency response, that will come later. Now, to get that information from the transfer function, as I told you, it is useful to factorize qs and ps into linear factors, and that's what I had done earlier for our numerical example. We factorized qs. Of course, qs was a first degree, so it came already in a factored form, only one factor, whereas the denominator was of degree 2, so it required some factorization. Now, so let me take the example now. So let's suppose g of s equal to, and I'll put that multiplying factor in front. So I'll write, as I did earlier, 0.4 into s plus 1 divided by s plus 2 into s plus 3. This is g of s. So what kind of information can I conclude from this g of s? Now, we don't know, of course, what u of s is until we know what u of t is. That is, until you are given a specific input function, let's say constant function, sinusoidal function, exponential function, t square or ramp or whatever, or some combination of these, until we are actually given ut, we cannot find out or calculate capital U of s, and therefore I cannot calculate x of s, because x of s is simply gs into u of s. I know g of s, but until I know u of s, I will not be able to calculate x of s with the intention of finding from it x of t, which is the response or a part of the response that we are looking at. However, the following can be said. Now, for most of the functions, input functions that one comes across, certainly for the constant function, for the unit ramp or a ramp with a non-unit coefficient, for the exponential function, for the trigonometric functions sine and cosine, and even for their products. We saw something like this earlier, a product like some power of t multiplied by some exponential multiplied by either sine or cosine of omega t. For an input which is as complicated as that, and in fact more complicated even, for an input which consists of a sum of terms of that kind, one can show that u of s will also be a ratio of two polynomials. What is it that such a function called a ratio of two polynomials? I told you earlier that it is called a rational function. It is called a rational function, and so u of s can be written as, I write n for numerator, a numerator polynomial n of s divided by a denominator polynomial d of s. So ns by ds. For many inputs, us can be found out to be a ratio of two polynomials or a rational function. Let us quickly run through familiar examples. For the constant function 1, u of s is 1 by s, that is a ratio of two polynomials. The numerator polynomial is just the constant polynomial 1, the denominator polynomial is s. For the ramp function whose value is t, for t greater than or equal to 0, the Laplace transform is 1 divided by s squared, again a ratio of two polynomials. For e raised to minus alpha t, what is the Laplace transform? 1 divided by s plus alpha. For sin omega t, what is the Laplace transform? Omega divided by s squared plus omega squared. For cos omega t, it is s divided by s squared plus omega squared. And I had asked you to calculate a few Laplace transforms earlier. So in many cases, the Laplace transform of the input is such that its Laplace transform is a ratio of two polynomials ns divided by ds. Therefore, let me write down the expression for the part of xs that we are looking at. Xs is equal to gs into us, but gs is already a ratio of two polynomials q divided by p, and u is also a ratio of two polynomials n divided by d. And so xs is a ratio of two polynomials again. The numerator polynomial is qs into ns, the numerator of g into the numerator of u of s, and the denominator polynomial is ps into ds, the denominator of the transfer function g and the denominator of the input transform u of s. So this is also a rational function or a ratio of two polynomials. Now remember what I told you to look up from the algebra books earlier, that a rational function can be expressed as a sum of partial fractions. Remember partial fraction expansion? Now there is only one condition which must be satisfied. If it is not satisfied, then you have to add something to what one is saying, and that condition is the degree of the numerator is less than the degree of the denominator. If the degree of the numerator, so I will write down here degree of the numerator, nr for numerator, is less than the degree of the denominator, then a rational function can be split into partial fractions, each one of which is a rational function indeed. And not only that, we can factorize the denominator into its linear factors, in other words find the roots of the corresponding polynomial, and then the partial fractions will look like what? Each term or each partial fraction is a rational function, and it so happens that the degree of the denominator for this part will also be greater than the degree of the numerator, but the denominator is a linear polynomial. So let us say it is s minus pk. Why p? Because p is to remind you of poles. In general, roots of the denominator polynomial are called poles, roots of the numerator polynomial are called zeros. So I have s minus pk in the denominator, and in the numerator a polynomial of degree 0, and therefore only a constant. And so my rational function can be expanded as a sum sigma of ak divided by s minus pk. Of course, this is not really 100% true. This is true provided the factors of the denominator are all distinct. So what are the things that one needs to look into? What if the denominator polynomial has repeated roots or has identical linear factors, several identical linear factors, a repeated root or a root of a certain multiplicity? That is thing number one. Secondly, what if the degree of the numerator is not less than the degree of the denominator, but it is equal or greater than? Now that can create certain problematic situation. So we will keep that aside for the moment. We will assume that the degree of the numerator is less than the degree of the denominator, and to illustrate the point we will assume that the factors of the denominator are all distinct, that is, there are no repeated factors. So let us consider that special case. It is not all too special, because it is not it's in very few cases that really we get repeated roots, exceptional cases really. In most cases the roots of the denominator polynomial will be distinct, there will not be any multiple roots. So let us look at that situation. I have x of s equal to qs by ps into ns by ds. Now think of the partial fraction expansion for this. Now of course, what are the factors of the denominator of this x of s? The denominator is ps into ds. So the factors are either factors of ps or factors of ds, factors of either the denominator of the transfer function, and what is the corresponding root called pole of the transfer function, or factors of denominator of the Laplace transform of the input, and we can call by analogy that also as a pole of the input. There is a difference. In one case I am talking about a pole of a transfer function, which is a ratio of two polynomials. In the other case I am talking about the ratio of, or rather the pole of the input, but what I mean is really the root of the Laplace transform of the input. Now there is one more assumption that I am going to make right now, and if I do not make that assumption, the situation once again is a little more involved, that ps and ds do not have any common factor. That is, there is no root of p which is also root of d, and conversely roots of p are distinct from roots of d. Suppose that also happens, then what? Then think of the partial fractions that come from the denominator polynomial p of s, that is, come from the factors of p of s. They will be of the kind ak divided by s minus pk. Therefore if I take the Laplace inverse of that part of x of s, what will that look like? What is the Laplace inverse of ak divided by s minus pk? It is ak into e exponential of pk into t. That is, it is an exponential function, because in general pk may be complex, and therefore this becomes a complex exponential, but that should not worry you, because for each complex root there is also a conjugate root. So for each term like this there is also a conjugate term, so together they give you a real function of time. So finally in your final answer you do not get any complex numbers or complex functions at all. So a root of ps or a pole of the transfer function, if it is not a pole of the input, it will give rise to a term like this, ak into exponential of pk into t. If pk is the pole, we get the corresponding exponential pkt. Now this is only one term in the total partial fraction expansion. What will be the other terms? There will be partial fractions corresponding to the other factors of ps and partial fractions corresponding to the other factors of ds. So this is not the only term, but if I assume that pk is the root of p and not of d, and it is a simple root of p, then this is one term that I will get, and there will not be another term with exactly the same pk, exponential pk. Other terms will have different exponents. Now what about this exponential pkt? We had looked at the graph of the exponential function earlier, and we saw that if pk is greater than 0, then the exponential function simply keeps on growing without limit. For example, e raised to t, e raised to 4t, and so on. So this means that the response will have a term like some number multiplying exponential which is growing, and therefore the response will keep on growing indefinitely as time passes. Now this is not exactly instability as such. We will see that the word stability of course can have different meanings. This is one meaning of stability, but it is one of the simplest meanings of stability. That is, the response will go on increasing indefinitely, or as one says, it will become unbounded, or one should rather say it will not be bounded. It will keep on growing as time passes. Now certainly we don't want that to happen in a physical system. Why? Not because we are afraid that the voltage in the circuit will build up from 1 volt to 10 volts to 100 volts to a million volts. Why are we not afraid? Because in practice, you will, before you reach that stage of even maybe 1 million volts or 1000 volts, probably your circuit will burn out. Or another possibility is the differential equation that we assume to hold for the system will no longer hold because of effects like saturation and nonlinearities and so on. Remember magnetic circuit saturation, I told you earlier that as you increase the field current, the field circuit may get saturated, that is the flux will not keep on increasing proportionately to the field current and it will saturate, it will almost become constant. So because of this unboundedness or growth, exponential growth is not going to take place at all, but because of it we will no longer be able to say anything about the system. The model that we had assumed will no longer hold. The system will no longer be described by that model when the variable x of t is large. This is true for most practical systems. No model is valid for very large values of the variables. Whether it's as simple a thing as a resistor and Ohm's law, V equal to Ri is okay provided the current is not too large. A very large current in the resistor will simply result in heating, and the heating will go on accelerating or cascading, and the resistor will finally burn out. It will no longer remain as a resistor obeying the law V equal to Ri. So a pole of the transfer function which is positive is bad from this point of view. On the other hand, if pk is less than 0, then what happens? Then we have the exponential function, but this time we have the exponentially decaying function. And we know already about this, that although this function never actually becomes equal to 0, but there is something called a time constant which we can associate with this pk, and in this case this time constant will be the reciprocal of the absolute value of pk, as we saw earlier. So if it is e raised to minus t, the time constant is 1 divided by absolute value of minus 1 or 1 second. If it is e raised to minus 2t, rewrite this as e raised to minus t divided by 1/2, and so the time constant is 1/2 and so on. And I have told you that after 5 time constants or 10 time constants, maybe 20 time constants if you wish, the function e to the minus 2t is almost 0. It's 10 raised to minus 5 or something of that sort, which can be ignored because all these variables are never known to a precision which is much greater than that anyway. So exponentially decaying is no problem at all. It only says that that part of the response goes to 0. But what we can find out from the root pk is the time constant, that is the decay takes place with a certain time constant that corresponds to the root pk. Now this is for the case when the factor s minus pk is such that pk is real and positive or pk is real and negative. What about one more situation? What if pk is equal to 0? If pk equal to 0, the corresponding term in the partial fraction expansion is ak divided by s. Now what is its Laplace transform? Its Laplace transform is simply the constant function ak, and therefore this part of the response will simply remain constant. But because it remains constant, it will keep on surviving as time increases. So it will contribute to the steady state, that is it will remain even when 20 time constants have elapsed or 100 time constants have elapsed, it will remain there till so long as the system is operating. So it contributes to the steady state, and we will see later on that this can contribute to the steady state error. That is, this kind of a situation can, not necessarily always will, but can contribute to a steady state error. Therefore a pole which is the number 0, or one says the system or the transfer function has a pole at the origin, because the complex number 0 in the complex plane is the origin of the complex plane, and so the language used is there is a pole of the system at the origin. If there is a pole of the system at the origin, then in the response there will be a constant term, and we will have to watch out because that could contribute to steady state error. So the three cases when the pole is real, and again on the pole 0 diagram, what will they look like? If the pole is in the right half plane, then pk is positive, s minus pk, pole is pk, so this is bad. If it is in the left half plane, that's okay. If it is at the origin, then we have to be careful. So if the pole or the root lies on the real axis of the complex plane, then these are the three possibilities that we have to consider. Remember, I am only looking at the case of non-repeated factors, or what are called simple poles. So there is only one pole at the origin and not 2 or 3, that is not repeated. The next case to consider will be, of course, when the pole is complex. In fact, before we consider the complex case, let us take care of the purely imaginary case. So what if there is a pole on the imaginary axis? Therefore the pole, let us say, is s j omega k, or the factor looks like s minus j omega k. I told you not to worry by the j, because there will be correspondingly a pole on the other half of the imaginary axis. In other words, there will be a factor which is s plus j omega k, and therefore in the transfer function really I would have had a factor like s squared plus omega k squared. So going backwards, if in the transfer function qs by ps, if in ps I have a factor s squared plus omega k squared, a quadratic factor with no s term, then it will correspond to a pair of poles like this on the imaginary axis. Therefore in the partial fraction expansion I will have two terms like ak divided by s minus j omega k, and ak, one can show that this will be ak bar divided by s plus j omega k, where ak will be a complex number. Now this thing looks like a complex expression, indeed it is. In fact, it is not complex, it looks like complex. When I take the Laplace inverse, I will therefore get ak into e raised to j omega kt plus ak bar into e raised to minus j omega kt. Now all of you have studied a little bit of communication engineering, and therefore you have seen this kind of a factor e raised to j omega t and e raised to minus j omega t before, and you know that when they occur in pair like this, in pair and with coefficients which are conjugate, this whole thing will reduce to what? It will reduce to a sinusoidal function. It will reduce to a function like a cosine omega kt plus some angle theta k. So in this case, when the poles are on the j omega axis, the Laplace inverse of this part, or therefore the response will have a term which looks like a cosine omega kt plus theta k. Is it good or bad? Well, it is not too bad, but it may be bad, because this means what? This trigonometric function is going to be there for all time to come. The trigonometric function does not become 0 either. So there will be a part of the response which will go on oscillating. It will go on oscillating till as long as you have the system on. The angular frequency of the oscillations is given by omega k. If the pole is at j omega k, the angular frequency of the oscillation will be omega kt. So if the pole is at j2, then I expect terms like cosine 2t to occur. Therefore the angular frequency will be 2. Correspondingly you can find out the period of the oscillation. So in the response then there will be a term which goes on oscillating forever, and that may be bad in some applications. It may not be steady state error which is constant, but it may be steady state error which goes on oscillating, and therefore that also may be bad. Now we have two remaining cases and we can dispose them off pretty quickly. One of them is the bad one, when there is a pole which lies in the right half plane. So let me write it as sigma k plus j omega k, and for that you know that there is a conjugate pole sigma k minus j omega k. So we have two linear factors of p of s which correspond to two poles like this, both of them are in the right half plane, both of them are complex. Then from this, what do you expect to get in the response? In the response there will be a function which will, of course the j omega part gives rise to the oscillatory function, but the sigma k part give rise to an exponential multiplying it, and therefore you will have a function which looks like e raised to sigma kt multiplied by cosine of omega kt plus theta k. Now this is bad, the cosine part is oscillating, there will be a multiplier in front perhaps. The cosine part is oscillating, but then it is multiplied by the exponential part which is growing. So this is again a bad situation. This means that after some time the model of the system will cease to be applicable, and therefore you can't say much about what will happen to the system. So right half plane complex poles are also bad. What about the remaining case? There is a pole here sigma k plus j omega k, where sigma k is negative, and a conjugate pole there. For example, minus 2 plus j3 is one pole, minus 2 minus j3 is another pole. What about the corresponding Laplace inverse? Corresponding to j3 there will be this cosine function, cosine 3t plus theta, and corresponding to this minus 2t there will be the exponential multiplier, but this time the exponential multiplier is not going to be bad, it will be a e raised to minus 2t cosine of 3t plus theta. The cosine part will go on oscillating, but the exponential part will go on decaying to 0, and so after 5 or 10 time constants this will be virtually 0. So this means that it will not contribute anything to the behavior of the system after sufficient amount of time has elapsed, and therefore one need not worry about it. So we have the following situation, that if we have the poles of the transfer function such that none of them are also poles of the input transform, and the poles are all distinct, no factor is repeated, then poles which are complex and in the right half plane are bad, poles which are real and still in the right half plane on the lying or the real axis are bad, poles on the imaginary axis are bad. A single pole or a simple pole at the origin may not be bad, but may have to be taken care of or may have to be examined because it may lead to steady state error. But poles in the left half plane, whether they are real lying on the negative real axis as it is called, or in the left half of the complex plane, complex and lying in the left half of the complex plane, they are all okay, and they would either cause oscillatory behavior which is damped or simply exponentially decaying behavior. Moreover, one can find out the time constant of the exponential decay by knowing the locations of the poles. So simply by looking at the pole zero diagram, if these conditions are satisfied, that is none of the poles is a pole of the input, then one can immediately figure out this information, that some parts of the response will behave in such and such a way, or because some parts of the response will behave in a bad way, the situation asks for some change. The system model will not remain valid, and therefore one will have to do something about the system to go further or to study it further. So this is where the knowledge of the transfer function can be useful, and I am not looking at a particular input. I have not said that let ut be this, then the response will look like this. I am not looking at that part of it at all. I am looking at only a part of a response that is determined by the poles of the system. But there is something else about which also we can say right away that this is going to be the case, and that is the following. There was one part of the response which looked like minus p bar of s divided by p of s. Remember that p bar of s involved the initial conditions of the response, rather not input. Input is q bar of s, ps is the denominator of the transfer function. What about this part? Now this part is such that the degree of the denominator is greater than the degree of the numerator, and therefore for this a partial fraction expansion is certainly possible. And again, if I assume that the factors are distinct, then the partial fraction expansion will be like this, and so I can say something about the Laplace inverse of this part. that is again another part of the response. And what is it that I can say? Exactly the same as I said earlier about the part coming from US into QS by PS, namely it will depend on the location of the pole of the system, pk. Is it in the right half plane? Is it on the imaginary axis? Is it in the left half plane? Is it on the real axis, or it's out in the complex plane? Accordingly, there will be a component of the response which will behave in such and such way. Either it is a bad behavior, so we have to do something about it. As we saw, doing something about it will involve usually feedback or making some changes in the system, or we can say something about the response which is okay, but we can say something specific like this is the time constant, this will be the frequency of oscillation, and so on. So there is something like that we can say. There is an interesting case that can occur here, and that is the following. It may happen that a factor of PS for some specific choice of initial conditions is also a factor of P bar of S. So for example, in our transfer function, the denominator had S plus 2 into S plus 3, and the numerator therefore was some polynomial minus P bar of S of degree 1. Now I leave it to you to figure out that one can choose values of d of x0 and dx0. These are the two values which determine P bar of S. One can find out a pair of values x0 and dx0, not one but many, such that the numerator minus P bar of S is simply say S plus 2. So if that is S plus 2, then what is it that we are to do? Well, the answer is you can cancel that factor S plus 2. That has to be justified because I am looking at a transfer function. I am not just writing some algebraic expression in school algebra and then cancelling a factor. Remember, these are all Laplace transforms of functions. They are not just algebraic expressions, or they are functions of a complex variable S which arise out of Laplace transformation. So one has to take care of it, but one can justify the cancellation. And so if I cancel the common factor, the numerator will be of degree 1, the denominator is S plus 2 into S plus 3. Suppose the numerator is just some multiple of S plus 2, then what remains will be something like A divided by S plus 3. Whereas if this had not happened, I would have had two terms like A1 divided by S plus 2 plus A2 divided by S plus 3. In place of that, I have only one term, A over S plus 3. What does this mean? In this case, in the case when there was no cancellation, e to the minus 2t will appear in the response as also e to the minus 3t. So there will be two exponentials with two different time constants in the response. Whereas if there is a cancellation, if the initial conditions are such that this happens, then one of the exponentials will not appear. So one says sometimes that the exponential will be suppressed, and these exponentials are also referred to as the modes of the system, and they are in fact called the free modes of the system. Why free modes? Because going back, this is what will remain when the input is 0. When the input is 0, x of s is simply minus P bar of s divided by Ps. There is nothing else. The input is 0, so the input terms have dropped out. It is only because of non-zero initial conditions that you have some response, and therefore such a response is called the free response, or the response with 0 input, and therefore these terms like e to the minus 2t, e to the minus 3t, which correspond to the poles of the transfer function, are called the free modes, or sometimes they are called the natural modes of the system. The word natural is supposed to tell you that it is under 0 input. So having a non-zero input is in some way unnatural, otherwise there is nothing natural about it. They are as much a part of the system for inputs and non-zero and zero inputs. So sometimes the free or natural modes of the response may get suppressed, and that will depend on the particular values of the initial conditions. So this is one thing that can happen. So let me show that I have Qs divided by Ps multiplied by Ns divided by ds, and this is only one part of the response that I am looking at. Suppose Ps has a factor s minus pk, and ds also has the same factor s minus pk. Then what? that is a pole of the transfer function is also a pole of the rational function, which is the Laplace transform of the input. Suppose this applies for the particular input. For example, the input may be simply e raised to pkt. If the input is e raised to pkt, the Laplace transform of it is 1 divided by s minus pk. And so I will have the situation that a factor of p is also a factor of d. Let us say the factor of p is simple, but it is also a factor of d. Now what? Now when I do the partial fraction expansion, I cannot consider the two factors separately. I have to take account of the fact that there is a factor here which is also a factor here, and so I should really think of the denominator as containing a term like s minus pk squared, and one can show from partial fraction expansion method that this will give rise to two terms, not just a divided by s minus pk as we had earlier, but also, and let us call it therefore a1 divided by s minus pk, and the second term will be a2 divided by s minus pk squared. So these will be the two partial fractions corresponding to a term like, or a factor like s minus pk squared in the denominator of x of s. So when a pole of the system is also a pole of the transfer function, we will get factors like this. What is the result of this? The Laplace inverse of the first term is simply e raised to pkt, which is bad or good depending on pk is in the right half plane or in the left half plane, etc. But the second part is the Laplace inverse of a2 divided by s minus pk squared. And what does it look like? Well, it looks like t into exponential of pkt. So it is no longer just the exponential, but t times the exponential. So is it bad or good? Well, it turns out that it is not really too bad. If pk is positive, then this is a growing exponential, and this multiplication by t increases its growth further. So it makes it from bad to worse. But if pk is negative, that is the pole is real and on the negative side of the real axis, then this multiplication by t does not influence things as t tends to infinity, because it requires some work, and you have perhaps calculated such limits in your calculus courses. If the limit of t into say e raised to minus 2t, the limit of this as t tends to infinity is fortunately 0. So this signal, although one part of it decays and the other part factor of it grows, the product goes to 0. However, it is not simply a pure exponential now, so I cannot talk about the time constant, and this function has a particular graph which I had asked you to draw long time ago. So if you have not done it at that time, sketch the graph of t e to the minus 2t as a function of time for various values of t starting from say 0, 0.5, 1, 1.5 up to maybe 5, and then see the trend. You will see that the function does go to 0, but before it goes to 0, it can exhibit some interesting behavior. It can become large. E raised to minus 2t is 1 and then goes to 0, but this product can exceed 1. Not in this particular case, but try to figure out when it can exceed 1. However, as far as long time behavior is concerned, or long term behavior is concerned, or the steady state behavior is concerned, this is no problem. The t is swamped over by the exponential decay, so it does not create any problems. Similarly, when we have oscillatory behavior, then the t will cause a problem if there is no exponential damping, but there is a problem already if there is no exponential damping, either oscillations or growing oscillations. So t will only make it worse. So this is not a terribly bad thing to worry about, a factor which is common to ps and ds. What if ps itself has a factor of multiplicity greater than 1? Ps itself has s minus pk square. Well, what we have done will convince you that if the pole is a good one, then s minus pk square is no problem. If the pole is a bad one, then the s minus pk square just makes the problem from bad to worse. And so the conclusion that we can draw is that on the pole 0 diagram, look at the poles of the system. If the poles of the system are all strictly in the left half plane, then no need to worry about this part of the response. Things are all okay. But if the poles lie on the imaginary axis, including the origin, or lie in the right half plane, then that is cause for worry. The system requires to be changed or some modification requires to be introduced, maybe some parameter needs to be changed or some feedback element is to be introduced or feedback element is to be changed, and so on. This phenomenon of things happening because of poles in the right half plane or on the j omega axis is vaguely referred to as some kind of instability, and it is connected with the boundedness or the response going to 0 or staying constant or being a sustained oscillation or growing indefinitely. This is what is connected with the poles of the transfer function. So just by knowing what the transfer function of the system is, you are able to say something about at least one part of the response. In fact, two parts of the response, because there is a part of the response that involves the polynomial p bar of s, that also goes with ps in the denominator, and the part of the response that comes because of the inputs presence, ns by ds, qs by ps, and in fact there is one more part of the response which is the other polynomial, which was q bar of s divided by ps, that also has terms contributed by the poles of p, and therefore the same thing will apply for that part of the response. So poles of the system can give you a lot of information about the behavior of the system as time increases without limit, that is after sufficiently long time or in the long term or particularly in the steady state, if there is a steady state. And therefore the transfer function is a very important tool for the study of systems. We are only looking at a part of the response, mind you. I have told you time and again that I am only looking at a part of the response. To find out the actual response, I need to know u of t. What is the actual input? I need to calculate its Laplace transform u of s, and then do all these calculations, use partial fraction expansion, and get an expression for the response as a function of time after inverse Laplace transformation. But before I do all that, I can find out from the poles of the system that this investigation is worth it or not worth it. If the poles are bad, there is no need to go further. You need to change the poles, you need to change the system to introduce some changes so that the poles are no longer bad. In other words, you check whether the poles are bad, and if they are bad, then don't analyze any further, change them to good poles. And we will illustrate this a little later when we go back to feedback and how feedback can change the behavior of the system. In particular, feedback can change bad poles to good poles, or the system was unstable in this sense, after using feedback it becomes stable. Unfortunately, feedback can also do just the opposite. Feedback can change good poles to bad poles in some cases, and therefore the system may be stable to start with, but because of improper feedback which has not been correctly selected, the system may become unstable. So we cannot just use feedback blindly, that is, say that no matter what, feedback is always good. No, we have to watch out there also. How much feedback or what kind of feedback is very important to find out and go into, because it can convert or remove bad poles or change bad poles into good poles, but it could also change good poles into bad poles, and therefore further analysis is required of the effect of feedback on the poles of the transfer function. Now I am going to look at our motor model once again, and now try to apply all of this to the behavior of the motor or its speed as a function of time, not in the steady state, that is not after sufficient time has elapsed the motor is running at a constant speed and so on, but in the transient state. What happens after the motor is turned on, switch is closed, the voltage is applied, the motor is initially at rest, it builds up its speed. In what way does it build up its speed? That is the transient behavior or transient analysis that we are going to do, and in doing that we are going to use the idea of the transfer function. And therefore, as homework, before we actually look at it, let us look at the situation once again. We had written down two equations for the motor speed control problem. Remember them? One was the armature circuit equation or voltage equation, the other was the torque or the mechanical equation. Now, since I am going to use Laplace transformation or Laplace transforms, I will change the notation a little bit. Remember that in Laplace transform work, it is convenient to let the function of time be denoted by a small letter like f of t or u of t for control people. The corresponding Laplace transform is then denoted by the capital letter ft u of s, or if there is an input u1 of t, then the corresponding transform will be capital U1 of s. Of course, in the English script, capital U and small u are sometimes difficult to distinguish in handwritten script, so one should be careful, but the presence of s tells you that I am talking about the Laplace transform and not the function of time. Fine. Therefore, I will change my notation. The applied voltage I had been denoting earlier by capital E for EMF or voltage and armature A of t. This is what I had been writing. So, I wrote EA of t equal to, remember the two terms, back EMF into omega t, and I am not writing omega motor, omega m, it is understood that we are talking about the motor. So, the applied voltage is the back EMF term plus the armature drop RAIA, but that was only in the steady state, and therefore, now I have to consider LA DIA dt. The only change that in the notation that I will now introduce is, instead of capital EA of t on the left hand side, I will write small ea of t. This is the applied voltage as a function of time. Maybe the applied voltage is just kept constant after the switching moment at 230 volts, maybe it is changed, maybe it is increased, decreased, or whatever it is. We will see all these things later on. So, small ea of t will denote the applied voltage, that equal to the back EMF plus the armature drop plus the armature inductance term LADIA dt. So, there is a derivative appearing here now. So, the homework is apply the Laplace transformation to the two sides of this equation, and from it get an equation involving transforms and functions of s. So, that is what will happen to the voltage equation. Then we have the torque equation. What was the torque equation? The generated torque. And now there is a conflict of symbols here. I cannot resolve it so easily. I need a symbol for the torque. I had used capital T, but then if I use small t, this small t is our preferred symbol for the time. So, what do I do? Well, let me stick with capital T with the understanding that if I write t of t or L of t, then this means the torque as a function of time, whereas if I write TL of s, then I am talking about its Laplace transform. Alternately, I can use some other letter other than t, but it is good to have t reminding us of torque. Okay? So, we have TL of t. No, that is not the equation. The equation starts with the generated torque. What was the generated torque? KT into IA. This is the torque produced by the motor because of the motion of the conductors carrying current in a magnetic field. KT into IA equal to, there are two terms earlier. What are the two terms? One was the load torque, of course, TL of t, plus the torque to overcome friction, which was Kf into omega. But now, because the speed may be changing, I have to consider the moment of inertia term, and I told you the moment of inertia is usually denoted by J. So, I have J into d omega dt. So, now there is a derivative appearing in this equation also, like the armature equation. Take the Laplace transform of the two sides of the equation, or apply the Laplace transformation to the two sides, and get an equation involving functions of s. Remember, there are derivatives here, d omega t dt and dia dt. Therefore, there will be initial values which will appear from these two equations. Then try to solve for what? Try to solve for omega s. The capital will denote the Laplace transform of the speed as a function of time, omega s, in terms of what? In terms of maybe TL of s and also EA of s. We had done this earlier for the steady state speed in terms of the load torque and the applied voltage. Now, we will have to find out the Laplace transform of the speed in terms of the Laplace transforms of the torque function and of the applied voltage function. And of course, there will be the initial values. What will be initial values? Initial value omega 0 of this motor. If the motor is starting from rest, omega 0 is 0. If the motor was already running, it will be that value. And what is the other one? The armature current, IA 0. Once again, if the motor was running, the initial value of the armature current will not be 0, but if the motor was at rest, then the initial value of the armature current is, find out whether it will be 0 or not. So these two will appear in the equation also. So find the expression for omega s in terms of load torque transform, applied voltage transform, and the initial values of the speed and of the armature current. This will be your homework.